Okay, so I think you're getting a sense of how we combine the physical changes with biological changes and chemical changes, right? It's a dynamic system, so diffusion is not a big thing, which means the CO2 uptake into the ocean or the outgassing as well will have a pattern, right? So if we look at the average flux of CO2 between the atmosphere and the ocean. Flux is, I think everybody has a sense. Basically, if you open a tap, water starts to come out. How much water comes out per minute or per hour, for example, is a flux. Whereas what remains in the bucket is a reservoir. It's the stock, right? So between the air and ocean, there is always mixing happening. There are turbulent exchanges of gases happening, not just CO2 plus, but also um, oxygen, nitrogen, methane, whatever else. Okay, so here is a map painstakingly put together by Taro Takahashi, and now lots of scientists using a lot of data over a long time. And this is made for a reference year. Because there is not enough data, they combine all the data and try to produce a mean picture. Okay, so this is for a reference year. So you can think of it as a climatology of air sea CO2 flux, global. Okay, so where it is positive, that's where the ocean is belching out CO2. Where it's negative is where the ocean is taking up CO2. So focus on your favorite region, the most familiar region for yourself, which I presume is the tropical Pacific, because we talked a lot about upwelling, about El Nino, La Nina, and so on. So you can see that here it's positive, which means CO2 is coming out of the ocean. I already hinted at it. There is upwelling in this region, and CO2 increases with depth. So when you upwell, you bring not only cold water and nutrient waters, nutrient rich waters, but you also bring out CO2 rich water. Okay, what does that do? That increases the partial pressure of carbon dioxide in the surface water, and the difference of partial pressure of carbon dioxide in the atmosphere and ocean provides a gradient. And that gradient, along with the wind speeds and other factors, some numbers like Schmidt number and so on, they determine how much CO2 actually goes out of the ocean. The Kuroshio extension region, the Gulf Stream region, and the cold waters up here in the Labrador Sea, and the Jin Seas up here in the Arctic, in the Southern Ocean, you can see that those regions are blue, which means that's where the ocean is taking up CO2. Cold water obviously is favorable for dissolving CO2. Warm waters emit, solubility goes down, but again it's the difference in PCO2, partial pressure of CO2 in the atmosphere and the ocean, and the mixing by the winds that determines all that. For example, here we have upwelling and cold waters, but you still have CO2 coming out because you have more CO2 coming from below and increasing the partial pressure difference between the ocean and the atmosphere, or yes, increasing so that it's belching out. So this is literally like opening the Coke can and then CO2 begins to escape because it's higher in the Coke can than in the air. Exactly the same idea with some details. Okay, so this is the magnitude of interannual variability. This is how the mean would look on a long time. So you can think of this as the weather if you want. Okay, how does it change from year to year? Obviously in this region there is high variability because this is the El Nino region. What would happen during an El Nino? We are saying during El Nino the warm temperatures move from the western Pacific towards the east. Trade winds get weaker, upwelling is reduced, biological production is reduced. So biological production is reduced means less CO2 is being fixed, but it's the upwelling that is reduced and decreasing the amount of high CO2 water coming up that is reduced. So the biology taking down the CO2 is again the biological pump that we talked about, and the water bringing up CO2 or bringing up less water coming up, less CO2 coming up is the solubility pump. So in these regions, even though it's a highly productive upwelling region, it is still the solubility pump that dominates. It's the upwelling and the high CO2 in the water that dominates the air CO2. Contribution of the biological pump is relatively smaller. Okay. In other regions where there's not a whole lot of biology, obviously solubility pump is dominating. Here there is strong biology, but still solubility pump dominates. Here the storms and the mixing matters a lot. So what we have to do is to track not only year to year change, but how things are changing over time. Is the East Pacific continuing to belch out CO2? Is it belching out more CO2 or less CO2? Are these high latitudes taking up carbon dioxide into the ocean? Are they taking up more or less? So the ocean's ability to continue to take up CO2 is obviously critical. Okay, so look at it again. Mixed layer dynamics, solubility cycle, fossil fuel uptake into the ocean, controls on the gas exchange like winds and turbulence, the biological pump, and upwelling, which is the advection of the CO2 into the surface layer, and so on. So obviously ice affects the AC exchange in addition to being a insulator of thermal exchange. They are also insulator of air-sea gas exchange. Remember that during glaciation and deglaciation we talked about CO2 decreasing and increasing in the atmosphere by about 100 ppm. So glaciers and ice would play a role in that. So increased anthropogenic CO2 emissions, generally the gradient of air-sea CO2 is changed, so it should drive ocean uptake. Temperature-driven solubility effects. If you warm the ocean, solubility is going to decrease. Okay, overturning circulation can weaken, which can decrease the uptake. And deep ocean waters are cold waters under high pressure, so they should hold more CO2. But if you change the circulation, you're going to change that dynamic as well. Biological production, you also have to remember that we will see a little bit more later. If we warm the ocean, stratification increases, which means the thermocline gets steeper, because the warm waters near the surface and cold waters below are going to be now having a steeper gradient. This would make mixing the colder nutrient-rich waters into the euphoric zone more difficult. So to first order, warming of the surface of the ocean should make it harder to mix up nutrients and should reduce production. We will see that in fact there is evidence that this happens. This shows how acidification comes about. So here we have let's say one CO2, let's say it's the current concentration of 415, or we start with 280 pre-industrial. So the partition of different parts of the CO2 cycle, H2CO3 would be 8, HCO3 minus is 16, 17, so the units are obviously not the same. Bicarbonate, this is carbonate, is 268, so that adds up to 1893 of the dissolved inorganic carbon. It's referred to as DIC, and the pH is at 8.15. What we are interested in is what happens when you double the CO2 or triple the CO2 in the atmosphere. So if you go from 280 to 560 or 280 to 840, you can see that H2 CO3 goes up correspondingly, but not quite double. Here it's gone more than triple, so it's a non-linear process because the partition into HCO3 minus and CO3 minus minus change very differently. It depends on reaction rates, etc., etc. So you can see that this only went up to 1850. H2CO3 almost doubled, but HCO3 minus only went up by some few percentages. And even when you triple the CO2, it went up by a little bit. Whereas the CO3 minus minus is dropping with increasing CO2, which is what we called acidification, and you can see that the pH has dropped continuously from double CO2 to triple CO2. Okay, so total dissolved inorganic carbon increases as you increase atmospheric CO2, but not proportional to the atmospheric CO2 increase, which means ocean's ability to take up CO2 drops overall. And just to show again that the gas exchange is one thing at the surface, but the advection of CO2 by the circulation is very important. So here we are again looking at a section through the Atlantic, this red line here, and you see our favorite deep water formation region pumping anthropogenic CO2. So you can see how much of the human produced extra CO2 is going into the ocean. So that's what this is showing. Deeper penetration there, smaller depths here, and deeper penetration into the subtropical gyres. This is in the Pacific where there is no deep water formation, so the gyres show deeper penetration. Again, convergence of water, downwelling in the middle of the gyres, so CO2 heat, everything goes down. Indian Ocean, same story. Subtropical gyre is only in the southern hemisphere, so you can see penetration of anthropogenic CO2 into the ocean. So everything is going to be related to the dynamics, because as long as we are moving energy from equator to pole, we are going to have winds and dynamics, so that's going to determine atmospheric circulation, ocean circulation, and hence patterns of heat uptake and CO2 uptake and other substances.